Hello everyone and welcome to another video. Today I'd like to continue our discussion on ordinary differential equations, but I'd like to look at a more general mathematical concept that we'll see can be applied to this scenario, but I want to keep the discussion today a little bit more general because this really is a mathematical concept that isn't necessarily constrained to just ordinary differential equations. And this concept that I'd like to talk about today is the idea of partial fraction expansion. And to keep me from having to write this out all the time, let's just reduce this and abbreviate this as PFE, okay? So partial fraction expansion is also sometimes known as partial fraction decomposition. You might see it under this name. Decomposition, okay? So the idea with partial fraction expansion or partial fraction decomposition is that you'd like to take a ratio of expressions in an independent variable like s. So for example, you might have some function of s, f of s, right? This could be a polynomial, this could be something more complicated, who knows what it is, but you've got a ratio of this polynomial, or sorry, this expression in s over some other expression in s here. And what we want to try to do is we want to try to break that down and make it look like the sum of a series of simpler expressions. So let's just write it like this generally. So something like f j of s over gj of s here, and you just sum over j. Okay, so we're going to see that all we're doing here is you have something complicated on the left and you want to try to break that down into a bunch of simpler ratios or simpler fractions, hence the name partial fraction expansion. We're going to try to expand the left-hand side into a bunch of simpler right-hand sides. And we're going to see that this is exactly going to help us, and it's going to be very useful when we start trying to look at inverse Laplace transforms in the context of ordinary differential equations. So we're going to take a look at that in a second. But let's get a little bit more concrete, right? This is a general idea. So typically the ones that we're going to look at, typically the left-hand side, remember, we're talking about ordinary differential equations a lot, and I think we saw a lot of these complex functions, let's call them capital F of s. And these, a lot of times, were expressed as the ratio of polynomials. So let's write this here as maybe like a b of s over an a of s. So in this case, we're not saying they're just general functions of s anymore. We're saying that here, b of s and a of s, these things are typically polynomials in s, right? And typically the class of functions that we want to consider here are the order of b of s is not greater than the order of a of s, right? So the order of the denominator is greater than or equal to the order of the numerator. That's typically the types of the family of functions that we want to look at here. So just as a quick example, just to make this concrete, you know, let's make something up. Let's make up one of these ratios that obey this rule. So I don't know, how about something like s cubed plus 3s squared plus, minus, I have in my notes here, minus 2s plus 2 all over 3s cubed minus 2. Right? So the top polynomial here, this is b of s, and the bottom polynomial is a of s. Here. And as you can see, the ratio, the order of the denominator is 3, the order of the numerator is 3, so we're great. So again, typically what we're going to assume here is that, that you typically have more poles effectively than you have zeros. Okay, so in general, the first step that we typically do with partial fraction expansion here, so the way to get started here, let me write this down. So to get started, one of the easiest things to do is to factor this polynomial into what's known as ZPK, or zero pole gain form. So let's say to get started, you want to factor into the zero pole gain, aka ZPK format. So all that means here is you might want to try to rewrite this f of s as, well, we know that this numerator polynomial, right, you could factor that into an s plus z1, s plus z2, s plus z3. right? We know it's a third order polynomial, so there are 3 roots to it. Roots at z1, z2, and z3. I guess technically at negative z1, negative z2, and negative z3 here. Similarly, down here in the denominator, it's of order 3. So again, you've got s plus p1, s plus p2, s plus p3, right? So you have zeros, you have poles, and also you might have a constant gain pop out of here, okay? Right? So here's where you get this term of zeros, poles, gain, or ZPK format, okay? So this is typically what we're going to do here, and what we're going to see is that once you get this in zero pole gain format, you're going to learn a lot about what type of partial fraction expansion that you're going to want to apply. So once you have it here, you're going to examine the poles, and we're going to see that you're going to usually fall into one of 3 categories. So we're going to have to consider these 3 cases. Cases / categories, classes, however you want to think about this. So what you can see here is one thing that could happen with all these poles is that you have distinct real poles. Okay? So I guess just to graphically draw this here, if we draw this on the real imaginary axis, if you were to go ahead and do this factorization here into ZPK format, and you notice that all of these poles are somewhere like here, 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 something like that. They're all real and they're all distinct. There are no double poles. There's nothing that are lying on top of each other. You'd be in this case, okay? The second thing that you could have are repeated real poles. Okay, so maybe we should have labeled this. Here's kind of class 1. And then, yikes, I did not use my whiteboard space well. Maybe let's draw it up here. Sorry, this was not planned out really well. So class 2 is you could have poles here, here, and here, but then you could have a case where there's a double pole. There's 2 of them overlapping, or maybe you have, heck, even maybe you have 3 of them, and then maybe you've got a multiplicity of 2 over here. But long story short, you've got a situation where there are multiple poles at the same location, right? That's class number 2. Okay, and then finally, class number 3 that you might end up with is you could have complex conjugates. Okay, so again, that would look something like class 3 is if you were to have poles that were complex conjugates of another, so they were imaginary. And I guess technically you could have now class 4 where you would have repeated complex conjugates, but you're going to see that this is going to give you enough information and enough know-how on how to tackle that case as well. So these are the 3 different cases that we want to assume for how to proceed. Now, the first thing that might pop to mind here is, okay, if somebody throws this at you, how are you going to factor it into the ZPK format, right? You're going to have to find the roots of the roots of the numerator here in order to get the zeros. Then you're going to have to find the roots of the denominator here in order to get the poles, right? So if I were you, I would run to some numerical package like MATLAB or Mathematica. And actually, if you're interested, we've got a video right over here talking about how to factor a polynomial using MATLAB or Mathematica, or actually, heck, even a TI-83, like an old school graphing calculator. So that will allow you to figure out which one of these cases you're in. So what I'd like to do now is I'd like to consider now each one of these 3 cases in turn and perform partial fraction expansion for each one of these. So give me a second to erase the board, and then we'll jump into the first one here in the case where you have distinct real poles. All right. So let's go ahead and take a look at case 1. And this was a case where we had distinct real poles. Okay, so in this case, what we're saying is that the complex function we're interested in, again, is a ratio of polynomials in S. And we're going to say a B of S over an A of S. And in this case, since the roots of A of S, or the poles of this function F of S, are distinct real poles, we are going to propose a particular form of the partial fraction expansion that looks like this. What we're going to try to do is we're going to try to break up this polynomial into a1, some constant, over S plus P1, where P1 is the pole location, or I guess technically the negative pole location. Basically, this is one of the poles of A of S, and then you have a distinct second real pole, an S plus P2. So again, in this case, P1 and P2 cannot be the same, and they have to be completely real. plus yada, yada, yada. You're going to do this all the way down to an over s plus pn. Okay, so what we're doing here is we're going to take this polynomial which has n roots, and we're going to propose that there is a way you can break it up into these n simpler ratios, right? That's the concept here with partial fraction expansion. For the case of distinct real poles, we claim we can make the left-hand side equal the right-hand side, okay? So how are we going to do that? Again, I think the easiest way to look at this is to just look at a concrete example. So in this case, let's consider an f of s, which looks like this. How about s squared plus 8s plus 15 all over s cubed plus 3s squared plus 2s. Okay? All right, so here is our complex function. Again, we see it is a ratio of polynomials, right? We got a second order polynomial on top of a third order polynomial. So the first step, right, we said was to find the roots of the denominator, right, of a of s, which is basically the same thing as find the poles of the system, right? Because we need to understand, are we in the case of case 1 with distinct real poles, case 2 repeated real poles, or case 3 complex conjugate pairs, okay? So again, I hope you watched our video on how to find roots of the polynomial, right? You do this in MATLAB or Mathematica. If you come here to MATLAB, I'll just write down the code. I don't think we need to go over and look at it, but whoops, sorry, that's roots with an S, right? You tell it I want the roots of this polynomial. So this polynomial in vector form, it's 1, 3, 2. Don't forget the 0, right? This is really plus 0 here, right? And you plug that into MATLAB, and this is going to say that you've got poles here. It's going to return and say your answer is 0, -2, -1. Okay, same thing. You can also do this in Mathematica if you want, but let's sketch out what that means. So again, if we were to draw this out in the real imaginary axis, okay, you've got a pole here at the origin. There. You've got a pole here at -2, and you got a pole at -1, right? This is what it looks like, okay? So let's call this, how about pole 1, pole 2, pole 3. So here's pole number 1, here's pole number 2, and here's pole number 3, okay? So we see that, yes, we are in fact in this case 1 where you have distinct, right? None of them overlap, and they're all on the real axis, okay? Now, the other thing that we should note here is, okay, you have a pole number 1, at s is equal to 0, right? So really what that means is up here, this P1, right? P1 is 0, okay? That's nothing fancy. Pole number 2, right? We said this is a pole at s is equal to -1 here, right? What this means though, again, this is where you gotta be a little bit careful about the sign, the sign. Over here for this P2, it means P2 is actually a +1, right? So this is +1, right? Similarly, pole 3, right, at s is equal to -2, this implies that your P3 is actually at +2, right? So again, this is a real easy place where you can screw up the sign. I just want to explicitly write this out, okay? So what we're going to do now is we claim, let's first go ahead and rewrite this expression by just factoring the denominator, okay? So let's just factor the denominator. Okay, so what we're going to do is I'm going to leave this thing, the numerator, untouched. It's going to be s squared plus 8s plus 15, right? And now I want to factor the denominator into these pole locations. So this is going to look like s plus 1, and s plus 2, right? Now, the one real quick check that you might want to do is you might want to expand the denominator out and make sure it exactly equals what you had earlier. Because what if the example over here was something like with like a constant in front of it, right? You go through this entire process, you will still get the exact same poles, right? This constant does not affect the pole locations or the roots of that polynomial, right? So you could go through all this, and then you might really be tempted to just do this. You might just say, oh, here's the pole at 0, pole at -1, pole at -2. But you have neglected this 2, right? Or this constant gain here, right? So remember, you're trying to get this in ZPK, or zero pole gain format, right? Don't forget this gain. Here's another very easy place where you can screw up and lose this factor here, okay? So in this case, I chose an example where this doesn't manifest itself, and maybe I should have chosen an example where you would have to do this, but in this case, we're okay. So we don't need to worry about that extraneous gain. But again, the idiot check here is at this step, just go ahead and expand this thing. Make sure you have rewritten f of s in an exactly equivalent form, right? So in this case, they're equivalent. This is the same thing as this, okay? So, so what we're gonna propose now is we claim that you can rewrite this in this format, right? So what we're gonna claim is I could rewrite this thing as sum a1 over s plus p1 plus an a2 over s plus p2 plus an a3 over s plus p3, right? And now we already know what our p1, p2, p3 are, so we can make that substitution. So we know that this is a1 over s plus 0 plus a2 over s plus 1 plus a3 over s plus 2. All right, so here we go. The game now is basically, let me just circle this, right? Here's what we've got, the original ratio of polynomials. Here's the proposed expansion, or the partial fraction expansion of this more complicated expression. So the game right now is literally just find a1, a2, and a3 to make the left-hand side equal to the right-hand side. That's all we're going to do right now, okay? So there's a couple of ways we can do this. Let's go ahead and I'll erase some of this to get a little bit more room, okay? So let's look at 2 methods of how to do this, and really they're very similar. Actually, I guess I can get rid of this whole header. We know we're in this case 1, and within this case 1, we're going to look at 2 methods to find a2. So let's go ahead. I'll just write that down. So consider 2 methods to find a1, a2, and a3. Okay. So method 1. Let's refer to this as the multiplication method. Okay, so method 1 here, all we're going to do is, let's again rewrite the left-hand side, which is s squared plus 8s plus 15 all over s plus 1, s plus 2, okay, is equal to the other side, and I'm going to leave a little bit of room right here. Okay, so this is a1 over s plus a2 over s plus 1 plus a3 over s plus 2. Okay, all right, so the multiplication method is we're going to try to get each one of these a1, a2, a3 one at a time. So to get a1, what we're going to do is we're going to multiply both sides by this term that's associated with a1, namely the s, okay? So what I mean by that is let's multiply this side by s and multiply the other side by s, okay? Now, when you do that, what's handy about this is, check this out, right? This s is going to cancel this s here, okay? So rewriting this, we end up with what? We end up with s squared plus 8s plus 15 all over s plus 1, s plus 2, right? That's what the left-hand side becomes. And the right-hand side is just, what? It's a1, no, actually, it's just a1, right? Because by the time you distribute this s through, it then knocks it out, so you end up with an a1 plus an sa2 over s plus 1 plus an sa3 over s plus 2. Okay? So this has to be true for all values of s. So let's pick a specific value of s. And in fact, what we're going to do is we're going to pick the s value that's associated with this pole, with pole 1, okay? Because we're trying to find a1. So in other words, this has to be true at s is equal to 0, right? This is the pole 1 location. Right? So basically, plug into these expressions, s is equal to 0, okay? So what we end up over on the left-hand side, we end up with what? A 0 squared plus 8 times 0 plus 15 all over 0 plus 1, right, times 0 plus 2. Right? That's what the left-hand side is. And now, this is where the beauty comes in. Check out the right-hand side. This, we end up with, well, I guess a1 plus, what, this is all 0, right? Because we're evaluating it at s equals 0, so this knocks it out. And same thing here. This s is going to knock out this term, so here we go. And you look at this, all we're ending up with is a1 is equal to a whole bunch of numbers, right? In fact, you work this out, I think it's just, what is it? It's 15 over 2, right? So here we go. We got ourselves a1, right? And tell you what, let's put this over, maybe I will, let's erase this, and maybe let's write down our results over here. I want to save that because we can easily, I think you're going to see the pattern very quickly. Right, so we ended up with a result of a1 is equal to 15 halves, or, right, what is that, 7.5? Okay? Okay, so now all you got to do is repeat this process, except, you're probably going to hate me for doing this again. I know it's hard to do in your notes, but let's get back to our starting point. That, right? Okay, so again, here's our left-hand side, is the right-hand side. So the same thing, let's go after a2 now. So to get a2, I'm going to multiply the left and right-hand side by this term right here, right? The s plus 1. So here we go, s plus 1, and then s plus 1 on this side, right? And again, the beauty here is this s plus 1 is going to cancel, whoops, that should still be an s, right? It's going to cancel this term here, okay? So the left-hand side, it becomes, I can quickly just modify this, like this, right? And the right-hand side, let's distribute this s plus 1 through, and you get a very similar story, right? You again, what do we get? We get s plus 1 a1 all over s, plus, I guess this just becomes a2, plus s plus 1 a3 all over s plus 2. Okay? Great, and we're going to make the exact same argument. The left-hand side has to equal the right-hand side for all values of s. Let's conveniently choose a particular value of s. Namely, we're going to choose s is equal to minus 2, right? Which is the pole 2 location, right? And what happens there, which makes this so great, is, okay, check it out. Again, what we end up with is all I got to do is plug in s is equal to minus 2 everywhere. So I get negative 2 squared plus 8 times negative 2 plus 15 all over negative 2 times negative 2 plus, wait a second. Did I? No. Oh, yeah, sorry, I'm an idiot. I got too excited. Negative 2 is not the pole 2 location, right? Negative 1 is pole 2's location. Whoops, there we go. Right, I know that divide by 0 is throwing me off. Okay, sorry, here we are. Okay, so this is actually negative 1 squared plus 8 times negative 1 plus 15 all over negative 1 plus negative 1 plus 2, right? So the left-hand side is just numbers here. And again, over here, the beauty about this is when s is equal to negative 1, check it out, right? This becomes 0, so we knock out this whole term that contains a1. We get a big fat 0 plus a2. And same thing over here. When s is equal to negative 1, you take out this numerator, so this is a 0. So again, a2 is just a bunch of numbers. And I think the number that this particularly comes out to be is minus 8, right? So great. Here we go. a2 is just negative 8. Okay, and here you go. I think you've seen the pattern at this point, so let's just go ahead and for completeness, finish out the example. Maybe I will erase some of these things. Yeah, I tell you what, let's just erase all this. Okay, get back to where we were. Okay, so here's the original. I guess this should be an s plus 1. Okay, so here we go, back to the start. And again, same game. We just need a3 now. I need this, so I'm going to multiply the left and right-hand side by the term here that's associated with the a3, which is this term s plus 2. So s plus 2, and then multiply the other side by s plus 2. And again, the beauty is this takes this out, those cancel. So the left-hand side is just s squared plus 8s plus 15 all over s plus 1. right, is equal to s plus 2 times a1 all over s plus s plus 2 a2 all over s plus 1 plus a3, right? And again, we'll make the same argument. It's got to be true at s is equal to -2, which is pole 3's location, right? So we end up with, this is just -2 squared plus 8 times -2 plus 15 all over -2 times -2 plus 1 is equal to, again, this term gets knocked out, that term gets knocked out, and we end up with just a3. So at the end of the day, we end up with a3 is equal to 3/2. Okay, so here we go. a3 is 3/2. Great. So there you go. This is one way to go ahead and get the partial fraction expansion. So at this point, what we claim is this original expression over here, what we were calling f of s, right, can be rewritten as, what is it? It's 15/2 all over s plus, I guess, a -8 over s plus 1 plus 3/2 over s plus 2. And I think if you go ahead and run over to Mathematica or whatever you like to do and expand this and check, you will see that yes, this is exactly the original expression, right? Okay, so tell you what, keep these in mind. Tell you what, let's box up our coefficients. These are what we solve for. And let's go ahead and look at method number 2. So give me a second to erase most of the board and we'll look at another way to get these exact same results. Okay, so method number 2 that I'd like to consider in this case of real distinct poles here is what I'm calling the coefficients method. Okay, so again, the idea was, here's our f of s that we had written out into factored format, right? So it's s squared plus 8s plus 15 all over s plus 1, s plus 2, and we had claimed that we would like to expand this into something that looks like this, a1 over s plus a2 over s plus 1 plus a3 all over s plus 2, right? Okay, so with the coefficients method, let's examine the right-hand side and let's just get a common denominator down here, okay? So this is going to be what? I think it's a1, and then I got to multiply this by s plus 1, s plus 2, right? This would be, and then now this term here, right? So I got to go a2 and then multiply it by this and this. And then I got the last term, which is a3, and I got to multiply it by s, and then this one, s plus 1, right? So this would be all over a common denominator of s, s plus 1, s plus 2, right? Okay, so let's go ahead now and take the numerator, right? And all you want to do is expand that numerator. And you can see that it's basically going to be a second order polynomial in s, right? Because you see this is going to be a second order, this is a second order, you add them all together, you still get a second order polynomial in s. So I want to do two things at this point. I want to now expand the numerator, and then what I want to do is I want to collect the powers of s so I can write this thing as something s squared plus something s plus a constant, right? So I want to do two operations. I want to expand the numerator, and then I want to collect coefficients of s in, let's do in descending order. Okay, so I think you could do that right now by hand, but you know, this might be an excellent time to jump over to Mathematica and show how you can have Mathematica symbolically do these two operations of expanding this numerator and then collecting the coefficients of s. So tell you what, let's jump over to Mathematica real quick to do that.
All right, so here we are in Mathematica. The first thing we should do is let's just type in our expression. Let's call it num for numerator. And remember what we had is, I think it was a1 s plus 1 s plus 2 plus a2 times s plus 2 times s plus an A3 S plus 1 times S, or something like that, right? So let's go ahead and shift enter that, and you see here's our ugly expression. So the next thing we said is we want to expand this out into polynomials of S, so it looks like a normal second order polynomial. So that's an easy call to expand. Expand will take in a expression and literally expand it out as much as possible. So if I shift enter this, and maybe let's assign this to another variable, num2, you see, here we go. So this has just expanded it out, and now what I want to do is, you see, it did not group all of these like terms of S here. Okay, so instead what I would like to do is I would like to collect all of these terms of S squared and then all of the S's and then the constant. So let's go ahead and say num3 is, check this out, you can say collect, you give it some expression like num2, and I want to collect this in terms of powers of S squared and S. So that, if I shift enter this, you see, aha, look at this. num3 is exactly in the format that I want. So I've got a second order polynomial very explicitly, and I see here's the coefficient of the S squared, here is the coefficient of the S, and here's the constant term. Maybe while we're here, I'll show you one more operation. Let's say you want to programmatically rip off the coefficient of S squared. So, you know, instead of coming here and saying copy this and saying coefficient, coefficient 1, sorry, instead of saying this, right, where you have to manually copy and paste in these terms, right, that's not going to be very helpful. Instead, what you can do is you can programmatically pull those off. So I can say coefficient 1 is, you literally call, the function is called coefficient. You give it an expression, which is that thing, and you tell it which coefficient I want. I want the coefficient of S squared. So this will give me that coefficient. And tell you what, let's do more. Let's get the coefficient 2, right, is going to be the coefficient of S. And then I want the constant, maybe I guess to keep this consistent, let's call it coefficient 3. Now, you can't just, at this point, you can't really call coefficient, right, because what are you going to give the coefficient of? Like the 1? That doesn't work, right? So really what you want to do is you want to take this expression num3 here, and I want the constant here. So I basically want what's left over where S is 0 everywhere else. So the way I would do this last one is I would say coefficient 3 is num3, but then I'm going to replace everywhere I see an S with a 0, right? So that's what the slash dot notation would be. So if I shift enter this, you can see I can programmatically rip off the first coefficient, second coefficient, and the third coefficient. Okay. That being said, let's back up. This is really what we wanted to get in Mathematica, and this discussion on the coefficients was just a little bit of icing on the cake. Let's go ahead now and run back to the board and see how we can utilize this.
All right, so what we ended up with is we said that this numerator could now be rewritten like such. We said this was a1 plus a2 plus a3 s squared plus 3a1 plus 2a2 plus a3s plus 2a1 all over s plus 1, s plus 2. Okay, and maybe let's bring the left-hand side down, right? This was our left-hand side. So this is s squared plus 8s plus 15 all over s plus 1, s plus 2. Okay, so great. Now what we're in a real good position to basically solve for a1, a2, and a3 because we see the denominators are exactly the same. So now all I got to do is pick the a1, a2, and a3 to make the numerators the same. And in order to make those the same, I got to make sure that the coefficient of s squared equals the coefficient of s squared, which in this case is a 1, right? And then I got to make sure that the coefficient of s here equals the coefficient of s, and then I got to make sure that the constant term equals the constant term over here. So we see we end up with 3 equations and 3 unknowns. So we end up with a1 plus a2 plus a3 has got to equal 1, right? This was the s squared term. Then we end up with what? 3a1 plus 2a2 plus a3 had better equal the coefficient on the s, which is 8 here. So here, this was the coefficient on the s. And then finally, the constant term, which is 2a1, had better equal 15, right? This was the constant. right? And here you go, 3 equations, 3 unknown, and actually even better, 3 linear equations, 3 unknowns. Feel free, we can write this in matrix form if we want. We could get this as basically pull out the unknowns, A1, A2, A3 has got to equal, what do we got? We got a 1, 8, 15, and I'll just put the coefficients here. So this is a 1, 1, 1, 3, 2, 1, 2, 0, 0. Right? Something like that. And you turn this thing into a big AX is equal to B. Solve this with Gaussian elimination or an inverse, whatever you'd like, and you'd basically get A1, A2, A3 instantly, and you end up with A1 is, if you do that in Mathematica or MATLAB, whatever you like, it's 15 halves. A2 is -8, and an A3 term would be 3 halves, which is exactly what we had earlier in the other technique. So again, there's more than one way to ride this donkey. You can either do it the multiplication method or you can do it using the coefficient method. You get the same result. So at the end of the day now, we have figured out how to do a partial fraction expansion for the case of distinct real poles. I want to keep the discussion today at a kind of a general mathematical level of just how to perform the partial fraction expansion, but the next step in the process, which we are going to talk about in our future video, is using this to perform an inverse Laplace transform. So tell you what, let's leave it here, and that's a little bit of a teaser for keeping with us for our next video where we actually use this in the context of solving ordinary differential equations. Okay, so we saw how that worked for the case of distinct real roots. Let's go ahead, give me a second to erase the board, and what we're going to do now is let's look at the case where you have repeated real poles. All right, so now let's consider case 2, and this was the case where you had repeated real poles. Okay, so again, let's look at an example. Okay, so the example that I'd like to look at here is f of s. My complex function is s squared plus 2s plus 3 all over the quantity s plus 1 cubed. So again, if we were to plot this on the real imaginary axis, I mean, it's pretty simple to see. You got one pole here at -1, then you actually got a second pole there at -1, and you finally got a third pole there at -1. So there's actually a pole at -1 with a multiplicity of 3. So we're clearly in this case of repeated real poles, okay? So how are we going to solve this? Well, we just learned a technique to do it for distinct real poles, you know, so we learned how to use a hammer there. Maybe this looks like a similar nail that we can try to bang down using that same technique. So tell you what, let's first try to use the same method we did earlier. Spoiler alert, it's not going to work, but I'd like to see how this fails to give us a little bit of intuition. So let's try the same technique that we did earlier, either the multiplication or the coefficient method, right? So what we're going to do then is, okay, what that did is we claimed, or we thought that, well, let's see if we can rewrite this thing, our s squared plus 2s plus 3 all over s plus 1 cubed. Let's see if we can rewrite this like as an a1 over s plus 1, right? Plus an a2 over s plus 1 plus an a3 over s plus 1, right? We're just going to do this expansion, right? Okay, so now let's go ahead and try this out. Let's try method 1, right, which was our multiplication technique or method, right? Okay, so how did that work? We said, okay, the first thing you're going to do here is we're going to multiply the left-hand side and the right-hand side by the term associated with a1. So what we could try is multiply this by s plus 1 and multiply the other side by s plus 1, right? Okay, so this s plus 1 is going to cancel and knock out one of these here. So what we end up with is s squared plus 2s plus 3 all over s plus 1 squared, right? Is going to equal, what do we end up with over here? By the time you distribute the 3, you end up with an a1 plus an a2 plus an a3. Okay? And now what we ended up trying to do was, if you remember with the multiplication technique, we said, okay, this has to be true at s is equal to -1. Right? Because that was the location of the first pole associated with a1. Well, look at this. Right away, we get hosed here because we end up with the divide by 0. We end up with, what is this? Something minus 1 squared plus 2 times minus 1 plus 3 all over 0 squared. So problem, doesn't work, right? You could also try the coefficient method if you want, and you're going to end up with another problem. For example, so if you do the method 2, let's try this. You say, okay, let's try the coefficients technique. Right? So remember, what did we say there? We said, okay, try to get a common denominator on the right-hand side. Well, actually, if you see, the right-hand side already is a common denominator, right? This is what we had originally, right? Look at this. It's already a common denominator, so you end up with, let's write this out. So the left-hand side is still s squared plus 2s plus 3 all over s plus 1 cubed. And then what's a common denominator over there? Well, it's an a1 plus an a2 plus an a3 all over s plus 1. And now you're a little bit hosed here, all right? Because I guess you could try to multiply the top and bottom by s plus 1 squared. Right? And then try to match up coefficients. All right, and then you carry this through, and if you were to expand the numerator and do the similar thing that we did last time by collecting the coefficients, you would basically get this to be a1 plus a2 plus a3 s squared plus 2 times a1 plus a2 plus a3 s plus a1 plus a2 plus a3 all over s plus 1 cubed, right? So we made the denominators match up, but you can clearly see this numerator, these things are linearly independent. This is, if you try to do this and solve back substitution or a matrix form, however we did earlier, you're going to get a null, it's an impossible solution, right? This matrix is going to be rank deficient, so this is not going to work. So method 2, the coefficients method, also choked. So long story short, the reason this didn't work is because it's basically telling you this is not a valid partial fraction expansion. You will never be able to make this thing equal. So we need to propose a different form of the partial fraction expansion here to make this work. So give me a second. We'll erase the board, and then let's look at the type of partial fraction expansion that will work for repeated real poles. All right, so the type of partial fraction expansion that we need to use here in this case is we need to rewrite this thing as an a1 over s plus 1 plus an a2 over s plus 1 squared plus an a3 over s plus 1 cubed. Okay, so that's our game plan. So this is a slightly different version of the partial fraction expansion, and you see we basically repeat the roots up to the multiplicity of the given root. Okay, so now in this case we can start making some progress. So again, let's look at two methods to try to find a1, a2, and a3 to make the left-hand side equal to the right-hand side. So method 1 is, I'm going to call this the derivative method. Okay, so what we're going to do is we're going to multiply both sides by this term s plus 1 cubed. Okay, so we're going to take this side, the left-hand side, multiply it by s plus 1 cubed, and take the other side and also multiply by s plus 1 cubed. Okay, and we see, all right, this is nice because this s plus 1 cubed is going to knock out and cancel with that entire s plus 1 cubed. So the left-hand side is going to just be s squared plus 2s plus 3. Is equal to, okay, the right-hand side, we're going to be a little bit careful with this. So we end up with what? a1 times s plus 1 squared plus a2 times s plus 1 plus a3, right? Okay, so great. Okay, so what we can now do is, again, we got to make sure that this is true at all values of s. So let's choose a convenient value of s, and let's choose s to be located at the pole location of s equals minus 1. So what we end up here with is the left-hand side becomes what? Minus 1 squared plus 2 times minus 1 plus 3 is equal to, okay, at minus 1, this term goes to 0, so we have a 0 here, plus similarly here, this is a 0, and this is a3. So look at this, we got a3 right now. a3 is just equal to whatever that left-hand side comes out to. I think that's that's positive 1, negative 1, no, sorry, negative 2, 3. So this is 2, right? So we end up with a3 is equal to positive 2. Okay, so again, let's put this up here. a3 is equal to positive 2. Okay? Okay, and we'll save this and we'll work on the other terms now. Okay, so now for the second term, to try to get to A2, we're going to have to play a little bit of a trick here. So what we're going to do now is let's go ahead and differentiate both sides, which is hence the name of this derivative method. So differentiate both sides with respect to s. Okay, so in other words, I want to take d ds of the left-hand side, which was s squared plus 2s plus 3, right, has got to equal d ds of a1 s plus 1 squared plus a2 s plus 1 plus a3, right? Okay, so if we just go ahead and take the derivative of both sides, what does this side become? This is pretty easy. This is now what? 2s plus 2, there we go, is equal to, and now here's where this derivative is going to be nice because it's going to start knocking out some of these terms that we've already solved for. So this first part becomes, what is this? This is 2a1 s plus 1, right, plus a2 plus 0, right? There we go. I think that's what we end up with, right? So, all right, that is awfully handy. Let me just make sure I got that right. Yep, plus 18. Okay, great. Now we're going to do the exact same thing. So this has to be true at all values of s. So let's choose s is equal to -1, the location of that we're interested in, the location of this multiplied pole or repeated pole. So we end up with 2 times -1 plus 2 is equal to, I guess this becomes a 0. And this becomes just a2. So great, here we are. So in this case, we end up with a2 is just equal to 0, right? So great, we got a second term. Okay, so I think you can get the pattern at this point. Let's go ahead and take the derivative again with respect to s. So we'll take the derivative of this expression, or I guess you can think about it as differentiating both sides with respect to x, with respect to s twice. But let's just do it again. So another derivative. Okay, so we're just going to go again and DDS this thing where we had 2s plus 2 has got to equal to DDS of 2a1 s plus 1 plus a2, right? Okay, so what do we end up with here? This is just a 2 on that side is equal to this is just 2a2, or sorry, 2a1, right? Plus 0. Great. So here we go. a1 is equal to 1. So perfect. Here you go. Here is our partial fraction expansion of this original function. And you might say, well, I'll tell you what, to make this completely obvious, let's write it out. So we said this is going to be equal to 1 over s plus 1 plus 0 over s plus 1 squared plus 2 over s plus 1 cubed, right? And you might make the argument of, like, did you really simplify this, right? This was a third order denominator, and you still got a third order denominator over here. But if you look at this, what's nice about this is the numerators, these are all by themselves very, very simple expressions, right? Okay, so now, you know what? Let's go ahead and look at another method. So give me a second and we'll erase some of the board, and let's come back and look at another way to get this same result for the repeated real roots case. All right, so the other way you could do this is you could use method 2, which is basically the same coefficient method we did earlier. So remember, now all that entailed, or if you remember, what that entailed was getting a common denominator on the left hand or on the right hand side. So let's see, this needs to be an a1 s plus 1 squared plus a2 s plus 1 plus a3 all over s plus 1 cubed, right? So that's a common denominator on this side. So we play the exact same game, right? You take this numerator expression, you go ahead and you expand it, right? Then you go ahead and collect coefficients, and then you compare the coefficients of s in descending order. So that's what you'll end up with. So tell you what, let's, I don't think we need to jump over to Mathematica. Why don't you take my word that if you ran over to Mathematica, do the exact same operation you did, that we did earlier, you would end up with this looking like an a1 s squared plus 2a1 plus a2 s plus A1 plus A2 plus A3 all over S plus 1 cubed. Denominator is the same. So again, it is the same idea now. To make the left-hand side equal to the right-hand side, the coefficient of s squared has got to match the coefficient of s squared. The coefficient of s has got to match the coefficient of s. And the constant over here has got to match the constant over here. So again, you write this thing out in matrix form. I don't think we need to do it because I think it's very clear what's going on right now. And if you do that and write it in matrix form, you would end up with the same similar ax is equal to b, except in this case, it's not going to be singular. You know what? Tell you what, let's just do it. It'll take me 30 seconds. I should have just done it to start with rather than blathering on. Probably could have done it in the same amount of time. Okay, so we end up with what? The coefficient of s squared. So we got an a1 has got to equal 1. This is the coefficient of s squared. Then you got the coefficient of s, which is what? 2a1 plus a2 had better equal 2. This was the coefficient of s. And then the constant of a1 plus a2 plus a3 had better equal 3. All right? So writing this thing in matrix form, we're going to pull out the a1, a2, a3 is equal to 1, 2, 3. That's kind of funny in this case. So we end up with a 1, 0, 0, 2, 1, 0, 1, 1, 1. And you can clearly see this thing is lower triangular. So this A, x is equal to b, has a unique solution. This A is not singular here. Every single row is linearly independent. So you run this thing through your, inverse or whatever you want to do to solve for A1, A2, and 3. You get exactly this result. So here's another way to go about it. And therefore, we have gone ahead and found ourselves the partial fraction expansion for this case of having repeated real poles. All right, so let's look at our last case, which was case 3, which was when you had complex conjugate pairs. Okay, so again, an example that we can look at is, here we go, f of s is equal to s minus 1 all over s squared plus 2s plus 2. Here we go. So again, here is our b of s over a of s. Okay. So in this case, let's take a look at the roots of this. And if you solve for the roots of this, you're going to end up with poles here at s is equal to minus 1 plus I, and s is equal to minus 1 minus I. So again, plotting that out on the real imaginary axis, it's very clear to see that you've got poles that are now off the real line, so they've got an imaginary component. Okay. So in this case, the partial fraction expansion, I don't know if I want to call it a whole expansion, but really it goes with the theme of, remember, all we're trying to do is rewrite this original format of the ratio of polynomials into another format that is going to make our lives easier down the road when we start thinking about doing an inverse Laplace transform. So in this case, what we want to do here is, let's consider a general denominator here. So in general, right, the denominator, you could factor it and make it, well, not factor, but you could basically, if there was a gain in here in front, you could pull the gain out and just get it in a form that looks like s squared plus ds plus e is equal to 0, right? Here's the denominator. Here's a characteristic equation, I guess, of this expression. So again, all we're doing is write it in such a format that the coefficient of the s squared is 1, and you can always do that, right? So if this is the case, what we're going to do here, the partial fraction expansion, or again, the rewriting it into a more convenient form, is we're going to want to write this in a form of s plus alpha squared plus omega squared. Okay, so it's really simple. All you got to do is find out what are alpha and omega in terms of d and e. So you can solve this, 2 equations, 2 unknowns. It's not a big deal, and you're going to end up and see that alpha is going to basically be d over 2, and your omega is going to be square root of 4e minus d squared all over 2, okay? So if someone drops a denominator in your lap that looks like this, you know that it has complex conjugate pairs. Just run it through this expression and rewrite it in this format. So coming back to our example, right, we see easily that d is equal to 2 in this case, and actually so is e, right? E is also equal to 2. So running it through this formula is basically going to get you an alpha of what do we end up with? Oh gosh, this is actually really easy. Alpha comes out to be 1, and actually, gosh, omega also comes out to be 1. Geez, so maybe that wasn't the best example. But long story short, what we're going to end up with is that shows you that you can rewrite this. You know, here's the original expression, plus 2s plus 2. You can rewrite this thing. The denominator can now be rewritten as s plus 1 squared plus 1 squared. Okay, that's all we're doing here. So in this case, this partial fraction expansion, I don't know if I would call this much easier, but we are going to see later on when we come to the inverse Laplace transform that this format on the right-hand side is a lot easier to deal with than the left-hand side, okay? Although they're both equivalent, okay? So again, this discussion is actually pretty simple. We didn't do a whole lot. The magic is going to come on later down the road when we actually want to do an inverse Laplace transform. So luckily, this was actually pretty short and easy. So there we go. I think we're done. We did all 3 cases, and but before we leave, I want to look at one example of what if you had a situation where the order of the numerator was actually greater than the order of the denominator. All right, so the last parting shot is I want to look at an example with an, let's call it a quote-unquote improper complex function. So usually this adjective improper is applied to transfer functions, which are really a type of complex function. But, you know, mathematically, we can still examine this scenario. So in this case, let's say you had something like s cubed plus 5s squared plus 9s plus 7 all over s plus 1, s plus 2. Okay, so in this case, you see that the order of the numerator is 3 and the order of the denominator is only 2. This should be setting off bells, red flags, and warnings in your head if you're a controls person. We're going to see later on that this corresponds to some weird situations, but since this discussion today is just about mathematical partial fraction expansion and rewriting these complex functions in a more convenient, easy to understand format, we can go through this and it shouldn't be a problem mathematically. Now, engineering-wise, I think that's where it's going to come up to be a little bit of an oddity, okay? So in this case, what you're going to have to do is you're actually going to have to perform synthetic division to rewrite this slightly. So step 1 here is perform synthetic division. Okay, and that's outside the scope of this discussion. Maybe I'll do a video on this later, but long story short, when you perform synthetic division on this, you can rewrite this as s plus 2 plus s plus 3 all over s plus 1, s plus 2. Okay? Okay, so now what you end up with is this complex expression, which is actually proper, right? And this is the denominator is of order 2, the numerator is only of order 1. So in this case, you can exactly see right away, this is a case of distinct real poles or roots, right? There's a root at -1 and s equal to -2, right? So you could perform the exact same operation we did last time. And what we're going to do is you're going to want the terms in s plus, you know, that stays the same. And we're going to partial fraction expansion this term to look like an a1 over s plus 1 plus an a2 over s plus 2. Right? So you go ahead and you do your multiplication method, you do your coefficient method, whatever. You can get a1 and a2, and I will spare you the boredom of going through that because I think at this point you're able to do this. And I think what you would end up with is 2 over s plus 1 minus 1 over s plus 2. Okay, so here you go. So in this case, again, mathematically, there's no problem doing this, but I would like you to keep this example in mind here because we are going to come back and revisit this exact expression here in our discussion of inverse Laplace transforms when we see and ask ourselves a question of what does this physically mean? What does this signal kind of look like in the time domain? Okay? So, with that being said, I think this is a perfect place to leave it because if you remember today, all I wanted to do with this lecture and this discussion was consider the mathematical concept of performing partial fraction expansion, and that's just what we did for these 3 cases of having distinct real poles, repeated real poles, and complex conjugate poles. here. Okay, so with that being said, I hope you'll catch us at our next video where we are going to now take the last step in the process of applying the Laplace technique, partial fraction expansion, and then the last step is the inverse Laplace transform, and that's going to allow us to finally have a closed, a nice system and workflow for solving ordinary differential equations. So, with that being said, I hope you enjoyed the video. If so, please consider subscribing and hitting the like button on this video. It really helps me continue making these videos. And until I catch you at our next discussion, I will catch you later. See ya. Bye.